Thank you. So the title is Having Fun with Music and Keras. That's actually what we're going to do. We are going to, now let's see, let's have some fun. So my personal motivation, so why am I interested in music? So I play guitar myself, and I had spent, when I started playing the guitar, I spent hours and hours listening to records, finding out what chord was being played over and over and over and over again. It was horrible. Then during my studies as physics, then I learned that there's something like a Fourier theory, which can decompose a signal into all the frequencies. I thought, okay, I'm there. I just apply this Fourier theory to my favorite records, and I can just generate my scores from it. It turned out to be a little bit more complicated than that. And actually now, since we have this the neural networks and deep learning, we can actually start going in that direction and actually finally starting to achieve where I actually wanted already 16 years ago. So what are we going to do today? So I'm not going to download some music, apply Keras to it, and say, hey, this is a nice result. So instead, we'll build up a simple synthesizer, and we will be using NumPy for that. So you can also easily do it yourself and experiment with that. So I will also explain a little bit of, well, I call it music theory, but just a little bit of how to generate some music. And actually, we use a simple random number generation and use that to generate like an infinite data set with music that sounds like music. It's not something you can sell or anything, but it's just a nice data set. And I will use this generated data for some deep learning applications. And I'm mainly going to dive in on operations on the raw sound data. So I'm not going to do anything with MIDI generation. So typically a lot of the work nowadays is with MIDI and generate actual music, like that sounds nice. I'm mainly going to focus on the raw audio signal and how to process these events. So why would I take this approach? Why generate a data set if you can just scrape Spotify or whatever? Well, first of all, it's more fun this way. So we can actually start building a synthesizer NumPy, right? And since we're building it from the ground up, we actually have also a knob to turn the complexity. So I can start with just a single instrument. I can add a second instrument. I can add harmony. I have the whole spectrum of complexity that I can slowly switch on. And last of all, the data set of generated music is unlimited, so we never run out. We have infinite amount of data. So I've actually done, so we have, with Go Data Driven, we have these Fridays. I've actually worked on 3 cases, but I probably have only time to present the first one. And that's to single out an instrument when multiple instruments are playing together. So we have a song with multiple, with a guitar and some other instruments. Can we just get the guitar back? And the other case that I also worked on is to detect notes when they're being played. That's actually my initial thing that I was after. It's called solfège, and that's for a single instrument. And then also, I want to extend that model to use multiple instruments to actually split the whole the total waveform into the different instruments, with each instrument its own score. And on real music, so this is on synthesized music, and on real music we'll actually also, as a teaser, we will try this final part. So we have a full band playing, and we just get the guitar back. So let's start building the synthesizer. And but before we do that, let's take a step back. Who has worked with audio before? Okay, so a lot of people still learn something new. So so let's first. I have here a WAV file. I'll read it in using a nice function with SciPy, and I get 2 things. If you do that, you get 2 things back: a sample rate and a raw data. And if you look at the sample rate is 44,100, and that's the number of samples per unit per second. And this is typical for CD quality music. So this is what you will typically see if you will load it like that. Then if we look at the raw data, we have this, if you look at the shape, we have a 1D array with a lot of these samples. So here you have all the samples that are in there. If we just zoom in onto a small portion of it, we see a bunch of integers. So what do these integers mean? So these integers are actually the position, the intended position of your loudspeaker at that point in time. So whenever there's a minus, it's on one side of the equilibrium position, and this is just the position of your the intended position of your loudspeaker. Of course, your loudspeaker is not completely 100% linear, and it will have its own effect on the music as well. But this is sort of the idea of music. This is the encoding of music. So, as I said, we have these integers. Of course, we can convert these integers back to floating point numbers and have a little bit of more easy way to interpret it. Like 1 means the maximum volume, and so 1 means the maximum volume. And also, when we start using deep learning, it helps to have it actually scaled in the unit domain. Also, to note is that if we are using music, if we're looking at music and we're having a sample rate of 44.1 kilohertz, we're actually the highest tone in there is half of it. And actually, if you look at what frequencies people can actually hear, the highest frequency that we can hear is roughly, for young people, 20 kilohertz. And so it means that if you go above it, you will not it will not change the music by a lot, although there are some interactions between different frequencies. So let's do the normalization to unit domain already explained. So typically you can divide by the max, but it's better to actually divide by the max int, not by the max thing that you've seen in your data. So this is how it looks like. This is for roughly 5 minutes of music. A nice way, if you're ever going to work with audio in Jupyter Notebooks, there's this ipython.display functionality, and it adds a very nice widget. You can see it over here. You can just put in some array, say which sample rate was associated with it, and you can just play it. This is now between 40 and 50 seconds. This is the part that you basically saw here. So let's go to the next one. Let's zoom in 1 second. This is how it looks. If we zoom in even further. So you can already see that this is not an easy signal, right? This is it is a lot of noise. Everything is encoded. Music to me is very multidimensional, right? You have frequencies, you have movements and stuff like that. But everything is encoded in just this one-dimensional string. And how do you get it out, right? So that's the challenge that we're up to. So let's start building it now from the ground up. Let's start with building a simple synthesizer. Let's first generate a tone, and let's start with a sine. We have a sine over there. We generate a data frame, put the time in as a grid of sample rate, and generate a sine like this. This is everything that we're doing. Then I made for now I made 3 graphs. So here you have this is the all data. If you zoom out over I think 1 second, then this is how you zoomed into 0.02 seconds. And this is a spectral graph. This is this multidimensional thing that I'm telling about. So you have basically frequencies on this axis, and you have time on this axis. And whenever it lights up, it means this frequency is active. So if we're now generating one single tone, it means that we indeed have one straight line that we see in the spectral graph. And you can actually, I already mentioned this spectral, this Fourier transform, you can actually get this spectral graph by doing a Fourier transform. So if I just want to detect which note is being played by this simple synthesizer, I could actually use Fourier for this, because I can just pick up the max frequency over here, and I'm done. Okay, let's now add an envelope to it. So I'll have the sign over there. I multiply it by an exponential, as you can see over here. Then it looks like this. Zoomed in, it's still extremely flat, but you have this envelope on a slightly larger time scale. Also in the frequency, you see it slowly dampening. We get a little bit of a sort of a boring electric piano sound. Right? Well, let's continue. So we just generated one single sign. But actually, if we add multiple signs to it with an integer multiple of the original frequency, so you have the sign over there twice and triple the frequency over there, then those frequencies are called harmonics. So you have a fundamental frequency, which is the lowest, and then every integer multiple of that is going to be an harmonic. And if you add those two together, this will actually not change the periodicity of the slowest signal. So you will still perceive it as having the same pitch as the original. So I've made this function, additive synthesis, takes in a grid of t-values, a grid of amplitudes, frequencies, and phases, and you're going to basically add those signs together. And here I just picked some random values for amps, random integer multiples for the frequencies, and I'll put all the phases on 0, generate it, and you get a slightly more complex waveform over here. But you can still see and hear that it's the same pitch as we had before. It's slightly more, slightly brighter, more aggressive. And indeed, let's show, this was the original sign, this was the original sign, and this is the additive sound. So it's more bright, has more feel to it. Also, very interesting, our ears are not susceptible to phase. So if we actually, instead of these phases, we put uniform phases in it, we can actually see that we have a totally different waveform, but our ears actually don't hear the difference. It's the same, right? And on the so if you might hear some differences, it's due to the non-linearity of the speakers. But so there's because actually this has a higher output. So this is quite amazing. And if we now apply a decay on this additive sound, we get something that sounds like this. We're starting to get a slightly less boring electrical piano, I think. And we can, so that was that one. So let's also use a little bit of drums. So I will generate a kick drum, which is basically, I will generate a frequency that starts very high and then decays to a low value. So the frequency will decay like that, and it will also apply over that the tone. Will also apply this exponential decay, and then we'll see how that sounds. So this is how it looks like. So you can actually see that it's slowly. So this is a kick drum. Now let's go one step further. Let's generate a snare drum. So snare drum, let's start with generating noise. So be prepared for noise. So this is noise. Let's add some decay and the tone of the original bass drum that we had. And let's combine those together with an exponential decay as well. There we have it. So there's another technique that's called subtractive synthesis, and the basic idea is you start with a waveform that's not sine. For instance, in this case, I use a square waveform, and then this square waveform has already a lot of frequency content in it. As you can see, you see all these lines in the spectrogram, and it already sounds very well, very 8-bit, right? Like a Mario computer game or something. And then the idea is that you actually, it sounds a bit harsh because there's too many frequencies in there. So actually the idea is that you subtract frequencies from the spectrum, like here. So you will actually say all these higher frequencies, I will just damp them, I will remove them. And if you do that, so you can already see here, they're sort of removed, you actually get a slightly different waveform in it, and it sounds a bit more dark, a bit more friendly, right? And these synthesizers I will actually use for generating the music. Just to mention that we have just only scratched the surface over here. So there's a lot of things that you can do to make it nicer. You can add effects like distortion, bit crushing, delay, reverbs, chorus, stuff like that. You can. There's even a totally different way of FM synthesis where you that looks like well, it's different. And then you have a synthesis using sampling, where you actually put a piano sample in it and you compress it to get higher frequencies. And there's also physical modeling, where you actually model the string of pianos and model the resonances within a piano, for instance. And you can also use LFOs for modulation effects. So this is a whole field on itself, but let's now generate some music. So everyone knows this. This is a piano, a keyboard. There's 12 notes. One thing I want to stress, there's 12 notes. If you count them, and you get to the same pattern again, and then it repeats and it repeats and it repeats. So actually, if you look, if you take this formula to the 12th power, you see that you actually get a doubling of the frequency. So you get you're making a harmonic step. So, and that sounds very similar to the original note. So this is also, it's easy to implement all the frequencies of all the notes on a piano by just using this formula. And you have to sort of tune the original, you have to tune it using some basic frequency. And typically we use 430 hertz for that. So I made a small class that actually takes all this, does all this work for me. So I created here a note class, and you can see it has a frequency for 40, and we can also generate the frequencies of different notes, and it's just implementation of that formula. I also made a small function that generates the signs for me, so I don't have to do it anymore. So it can just generate a note, takes a note in, and generates it. And this is a D. And of course, if I can generate a D, I can also generate a scale like do, re, mi, fa, sol, la, ti, do. And here, those are the notes that belong to it. And I just generate the full 2 octaves. That's two times the repetition. And I'll basically, we can listen to it. It's a bit loud on that side, or could I still improve my synthesizer a bit? Or okay, so given that we have notes, there's also there are music rules for making chords out of notes, and given that same progression of notes, I can generate a chord that fits along with it. So that's so we have something that's already music. Let's try to make a basic improvisation, and we'll use a random walk for that. So, first, I want to have some chords, something that makes the music a bit nicer. I keep this one fixed, and this chord progression I take, which is one that's used most in pop music, and that sounds like this. Probably you all know one song that immediately fits within this chord progression. There's so many out there. So now add some melody. As I already said, I will use the random walk, but then through the skill, because the skill sort of governs which notes fits in, which fit nice together. And of course, since we're doing a random walk, I can also decide on if I want to make big steps or small steps and stuff like that. So I made a sort of tune to taste, no ML or no even statistical analysis involved there, just to tune these weights for making smaller and bigger steps by hand. So these are the probabilities that I used. And then basically, I don't want to continue growing up until infinite pitch. So I also sort of I mirrored whenever I was out of some range that I predetermined. And how does that actually sound like? It will not make me rich, but but I do have an infinite data set this way. Actually, I hate this music by now. I've heard it so often that. So let's go to the case where we'll be filtering out the melody from the combined sample. So we have this model. We're going to make a model that will take this input wave with 3 instruments, and we'll generate out only the melody part. So actually, if we look at it, it's very much almost like an autoencoder, right? It's not exactly auto-encoding, but we have this some original data going in, then we have some dense network in between, and we can generate the output again, but this is then a different output. So let's try it. So this will be our input data will look like this. I added the baseline as well. And then this is our target. So the model will just try to predict from X train, Y train. So how do I generate actually a training set from it? So I cannot just put in the full sequence of data, because that will be too much, right? So I have to sort of break it up into small batches. So what I actually do is I generate like 30 seconds or 12 minutes of data, and then I randomly sample some portions out of it. And then that's how I actually generate the training set. So let's try to make the simplest model that I can come up with, just a dense model. So on 1,000 data points, slightly more, let's just connect a dense model to it. So you can see here, there's just a dense layer, then prelude activation in between. We get indeed slightly, we are going to reduce it by a bit. And then we're scaling up again to at least have the same output dimension as our input dimension. How does that actually? We didn't train, we just initialized some random weights. So how does it actually sound? Okay. Not particularly nice, right? So this is what the randomness sounds like. Let's try to fit the model. And actually used only 2 epochs for it. And let's test the model. So this was original. And this was the reconstructed. Could be a bit better, right? Not particularly nice, but let's first try if it's overfitted or not. So we are going to generate a completely new data set in a different key with a different scale even. So actually, it's not remembering actually all the samples that it has seen, of course. But still, of course, if you would put some real music to it, it will be overfitted on this particular sound of the dataset. Okay, so this is sort of working, but can we actually make it slightly better if we get this thing to the top? So we had actually a very simple. Why isn't that working? Let's try this one. No, that one is working. So we had I think it's still. So let's now instead, we know about this Fourier transform, right? So we have this 1D sample, 1D stream of data, which contains all the information. Well, we have this Fourier transform that actually sort of makes it way more as how we perceive music. And also our ear is constructed in a way to detect these things. So it will help us to actually do that. So let's try that out. So again, we're using the same train and target. I will not explain that for you. And this is what I call the FFT branches model. So we start with the input. We then do an FFT within the model itself. Then we get a dense network on the actual values of the spectrogram, the highlights. But then the Fourier transform also gives you information about the phases of the signals. But as I said, we don't hear these phases. So this is on so then I construct again Fourier, the inverse Fourier transform, and that will be finally my prediction. So only here are going to be the weights of the model. So I will not go through it completely, but I've put it here. You can actually see that it's not so hard to do a Fourier transform within your network. You can just do that by using TensorFlow functionality. So let's continue. So again, how does it sound before training? Not so much different. And then let's continue. So actually, I needed here to do more than two epochs because, yeah, I just need it. And so let's actually start testing it. Before and after. So actually, I was actually happy when this happened. I thought, hey, this might be working. And well, let's try again on this different data set. That works as well. So I was thinking, can I actually do this on the real music? Can I actually do this full band with to guitar? Can I just using the same structure? So now this will be our X train. So you have a guitar and a band. And then only the guitar. And then use that to fit it. And will it still work? So this reconstructed. You can still hear a little bit of the drums sweeping through. It's not perfect. But it made me really happy when when I got to this level. There's just one disclaimer that if you use this, you also learn a lot about the backing track in itself. So there's also, if you use this on a different piece of music, you will still see that it has some issues with finding out what is actually the intended guitar. But it's a very nice starting point. There's one last thing that I want to try out. So if we use the model trained on the synthesizer, and we use that for the same purpose, does that actually work? you can definitely see that all the drums are still being fed through the network, right? It is not being filtered at all. So the drums were not part of my synthetic data set, so that you can imagine. But still, it picks up more the guitar from the music than the rest of the music. So it already sort of gets the notion of the main instrument, the melody line, out of it. So conclusions. So actually, what I really think, what I really liked about this project is that I created some playground where I can tweak my complexity of my things that I'm working in myself. And typically, we download a data set, we apply some deep learning on it, and then we see, oh, it's not working, or it is working, and then someone, you learn a lot from actually playing around with it and being able to tweak the complexity. Because I've been able to use techniques that I learned here at the customer as well, by just being able to explore, getting better insights on these algorithms. So that's my main takeaway for you. And that was